So our topic is work done during an adiabatic process. So before we start this topic, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you, and also press the bell icon so that you get notified when new video will be uploaded. Okay, and this is my Insta ID OJHALAKHYAJIT 123. This is my Insta ID. Follow me on Insta. So now let's start. So first, here you see, suppose a thermodynamical system undergoes adiabatic process or adiabatic change undergoes adiabatic change or adiabatic process from the state P1, which is pressure, V1, which is volume, and T is the temperature. So here you see T1 is the temperature, okay, to another state P2, V2, T2. Okay, so hope you have understood this. Now work done by the gas to increase in volume. Okay, work done by the gas for small increase in volume is given by dW is equal to PdV, pressure into change in volume. Now total work done during the process to change the volume from V1 to V2, that's going to be given by W is equal to integration of dW, okay, 0 to W, that means integration P dV, your volume V1 to V2, right? So now you see, let me copy this and let me go to a new slide. Okay, so here is the last step. So now you see, let me take this as equation number 1, right? Now we know during adiabatic process, during adiabatic process, PV to the power gamma is equal to constant. Let this constant be suppose K, say it is constant, okay, and here the gamma, just wait, give me a sec, this is P. Here the gamma is the ratio of Cp and Cv. Cp is the molar specific heat, at constant pressure, and Cv is the molar specific heat at constant volume, right? Now you see what we can do. From here we can write that P is equal to K by V to the power gamma. Now you see it can be written as K into V to the power minus gamma. This is equation number 1, sorry, not 1, 2. So using this value of P here, what we can do, using equation number 2 in equation number 1, we can have w integration from v1 to v2 p dv. So instead of p, we're gonna put this k into v to the power minus gamma, right? So we have used equation number 2, value of p here. Okay, so hope you have understood this. So now k is constant, so it can be taken outside the integration, right? So that's why we can write the k here, right? Now if we integrate it, then what we're gonna have k, so v to the power minus gamma plus 1 by minus gamma plus 1, which also can be written as 1 minus gamma here. So similarly, this can be written as 1 minus gamma, and we are integrating it from v1 to v2. So if we put those upper and lower limits, then what we're gonna have, k 1 minus gamma. So here we're gonna have, you see, v2 to the power 1 minus gamma minus v1 to the power 1 minus gamma, and this also can be written as 1 by v2 to the power gamma minus 1, and similarly this also can be written by as 1 by v1 to the power gamma minus 1, and you can multiply this k here and here also, then here we're gonna have 1. Now you see from this equation, from this relation, what we can write now. Since v to the power gamma is equal to constant k, so what we can write, v1 to the power gamma is equal to p2 v2 to the power gamma. We can write that way because we are taking two states, p1 v1 t1, and the system changes from this state to p2 v2 t2. That's why we can take p1 v1 to the power gamma, p2 v2 to the power gamma, using this relation, equation number 2, using this relation here, you see, right? So if we use this relation, let this equation be 3 and this is equation number 4. So using 4 in 3, so just wait, let me copy this equation number 3 and let me take a new slide. Just give me a second. So this is 3 here, this is a new slide, this is the equation number 3, and let me take equation number 4. So here is the equation number 4. Okay, so if we use this equation here, then what we can write now, you see, so if p v to the power gamma is equal to constant k, so these two must be also equal to k, right? So I forgot to write that k here, so let me write here k. So that should be k from this equation, right? So using 4 in 3, so we're gonna get w is equal to 1 by 1 minus gamma to the power p1 v1 to the power gamma divided by here we have to put p2 v2 to the power gamma by v2 to the power gamma minus 1 minus again p1 v1 to the power gamma by v1 to the power gamma. So I have used here this value and here I have used this value. So hope you have understood this. So now you see, if you cancel this one, then what you're gonna have, you're gonna have w is equal to 1 by 1 minus gamma. So here you're gonna get p2 v2 minus p1 v1, and if you make it gamma minus 1, then order will be changed. That's going to be gamma minus 1, right? And p1 v1 minus p2 v2, right? And also we know that equation of state, we know the equation of state that you see from the equation of state, PV is equal to mu RT. This is for isothermal, this is for real gas, ideal gas, for ideal gas. Okay, so we have taken here ideal gas, right? So now you see, and if we considering the system that we have taken, the system contains 1 mole of gas, that is mu is equal to 1. In that case, this equation can be written as PV is equal to RT, and so we can write P1 V1 is equal to RT1, and let me write this one here, and we can write P2 V2 is equal to RT2. Now let me use these two results here. So this is also, you know, expression for work done in adiabatic process, but if we use these two values, we will get another form of expression. So let me write that in the next page. Okay, so here you see, this was the expression for work done we have got. So now let me copy these two results. Here you see, so if we use these results, okay, P1 V1 is equal to RT1 and P2 V2 is equal to RT2. So work done will be equal to 1 by gamma minus 1 here, RT1 minus RT2. Okay, if you, instead of considering 1 mole, if you take the mu mole or n mole, then that n or mu also written here, can be also written. Okay, so that's why now take R common, R by gamma minus 1, then here T1 minus T2. For n mole of gas or mu mole of gas, you have to put here mu or n, whatever you take. Okay, so this is the required expression. So hope you have understood this. Thank you for watching. See you in the next video.